The context library provides current execution context specific to the message sender and message data primitives. Recall that these primitives are provided by Solidity. In situations where our smart contract is working with what are known as meta transactions, where the account sending the transaction and paying for the gas costs may not really be the actual user as far as our application's context is concerned. In such situations, which happen where there are relayers between the user and our smart contract, the functions implemented by this library help us distinguish between the user's context and the relayer's context. There's a simple counters library that allows a contract to declare new counters and decrement it. This is useful for doing things like tracking the number of mapping elements, for Ecdsa token IDs, for request IDs depending on the application context. And there are different functions, very simple ones, that let the contract get the current value of a counter, reset it to 0, and increment and decrement the counter by 1. OpenZeppelin has a create2 library that provides library functions to use the create2 EVM opcode functionality in an easier and safer manner. Recall from our discussion of the EVM instruction set that EVM has two instructions, create and create2, that allow contracts to programmatically create other contracts. This is in contrast to creating contracts by sending a transaction to the 0 address. So if we think of this as a deployer contract that is creating a newly deployed contract, then the create opcode uses the address of the deployer contract along with the state of the deployer contract in the form of the nonce of that contract account to determine the address of the newly deployed contract. Contrast to this, the create2 opcode does not use the state of the deployer contract at all. It does away with using the nonce of that account, and instead it only uses the bytecode of the newly deployed contract along with a value provided by the deployer contract known as the salt to determine the address of the newly deployed contract. So because of this change of not using the nonce, the address of the newly deployed contract becomes deterministic. So in this case, the deploy library function uses 3 parameters, the amount, salt, and bytecode, to create and deploy a newly deployed contract. The amount in this case is the amount of the ether balance the newly deployed contract will start off with. If one only wants to determine the address of the new contract without actually deploying it, there is a library function called compute address that helps one to do that. And if one wants to compute the address of this contract, if it is going to be deployed from a different deployer address, then there is a different library function, compute address, that takes in an additional parameter, which is the address of the deployer, to allow one to do that. So these are very interesting library functions that allow a smart contract to use the powerful create2 opcode to create new contracts at deterministic addresses. OpenZeppelin provides a multi-call library that allows a smart contract to batch multiple calls together in a single external call to this contract. And this function is multi-call. It takes in a single data parameter as shown here, and it returns a bytes array of all the return parameters from those multiple calls. So it helps this contract to receive and execute multiple function calls in a batch. And the benefit of this is that it is less overhead and makes it more gas efficient, because all these multiple calls are now packaged in a single call within the same transaction of the same block. OpenZeppelin provides a string library that allows one to perform some basic string operations. There is a toString function that converts a uint256 to its ASCII string decimal representation. There is a toHex string that converts it to an ASCII string hexadecimal representation. And finally, there is a toHex string that takes in a length parameter that converts a uint256 to a hexadecimal representation with a fixed length. OpenZeppelin provides an Ecdsa library. Recall that Ecdsa signatures are used very commonly in Ethereum smart contracts, and the signature itself has three components, V, R, and S, which are 1 byte, 32 bytes, and 32 bytes in length, making the signature 65 bytes. The EVM has an EC recover opcode, and Solidity has a similar primitive that supports this opcode. But that opcode allows for what are known as malleable or non-unique signatures, if you recall from our earlier discussion. And this library prevents that malleability of those signatures by providing a library function, recover, that is not susceptible to this malleability. And the way that it's made possible is that this function requires the S value or the S component of that signature to be in the lower half order and the V value to be either 27 or 28. So this becomes important depending on how the smart contract is using the signatures and if malleability is a concern or a risk for that use case. The recover function takes in the hash of the message and the signature component of that message and returns a signer address. So to sum it up, the EVM EC recover is malleable, which may be a concern depending on how the signature is being used in the smart contract logic. And this library provides a non-malleable way of using EC recover and a library function associated with it. The Merkle proof library provides functionality to help with the verification of Merkle tree proofs. Recall from our discussion in the Ethereum module that Merkle trees are data structures where the leaves contain the data and all the other nodes in the tree contain a combination of the hashes of their two child nodes. This library provides a verify function that takes in three parameters. It takes in the leaf, root, and a proof and returns a Boolean value, which is true if the leaf parameter can be proved to be a part of the Merkle tree defined by the root parameter. And in order to do that, a proof must be provided to this function that contains all the sibling hashes on the branch from the leaf to the root of the tree. So this is an interesting library that is used often where Merkle tree proofs are required within smart contracts. The signature checker library provides functionality that allows smart contracts to work with both Ecdsa signatures and ERC1271 signatures. We have talked about Ecdsa signatures that are signatures that can be created with the use of a private key, which is really possible only with externally owned accounts. And the reason for this is contracts do not possess or cannot possess a private key because all contract state is public. ERC1271 allows the concept of contract signatures in a manner that is different from Ecdsa signature. I would encourage you to look at this ERC if you're interested in the details. And this library becomes interesting for applications such as smart contract wallets that need to work with contract signatures and Ecdsa signatures. There is an Eip712 library that provides support for the hashing and signing of typed structured data as opposed to binary blobs. This supports the notion of an Eip712 domain separator, the details of which I would encourage you to look at the EIP itself and the source code of this library. This is again often used in smart contracts, and from a security perspective, what becomes interesting here is whether this signature includes the chain ID of the chain where the smart contract is deployed and being executed, and whether this also includes the address of the smart contract itself. Not using these two values within the signature can allow replay attacks if the contract is redeployed to some other address on the same chain or to a different chain. We'll revisit this in the security module, but this is something to be kept in mind. The Escrow Library allows a smart contract to hold funds for a designated payee until they withdraw them. And the contract that uses this as the payment method is its owner, and it provides three functions to allow this functionality. There is the deposits off function that returns the amount of the funds designated for the payee, and then there are the deposit and the withdraw functions themselves that are only callable by the owner. The conditional escrow library is derived from the escrow library, and as the name says, it only allows withdrawal if a particular condition is met. The withdrawal allowed function checks for this condition and returns true or false if it is met or not. And the withdraw function itself is of public visibility and does not have the only owner modifier here, but it checks the withdrawal allowed condition, and if that is met, it calls the base contract's withdraw function that has the only owner modifier. That's something to pay attention to. The Refunds Escrow Library is further built on top of the Conditional Escrow Library that we just discussed, and this allows holding funds for a beneficiary that are deposited from multiple parties, multiple depositors. And this contract has three states in which it can be. It has the active state, refunding state, and the closed state. Active state is when deposits are allowed to be made by the multiple depositors. Refunding is where refunds are sent back to the depositors. And finally, there is a closed state in which the beneficiary can make the withdrawals. The Ecdsa library allows one to determine if a particular contract supports a particular function interface. And this runtime detection is implemented using a lookup table. It provides two functions. The first one is for registering function interfaces. This is the register interface function. And the second one is to determine if a particular interface is supported, which returns a boolean, either true or false. OpenZeppelin provides a math library that has some basic standard math utilities that are missing in the Solidity language itself. There's the max function that returns the maximum of two uint 256 values. There's a minimum that provides the minimum of those two values, and then the average function that returns the average of those two numbers, which is rounded towards 0. Then there is the Safe Math library, which we have talked about earlier. This provides the basic math functions that are safe from overflow and underflow conditions because of wrapping. This has support for add, sub, mul, div, and mod functions. And the typical usage is done via the using directive, where you would see something like using safe math for uint 256, where the safe math library functions are applied to all variables of type uint 256 in that contract. There are The try-variants of these functions where instead of reverting, if the overflow or underflows happen, a flag is returned. And this is useful for exception handling. So this safe math library is almost absolutely required for smart contracts that deal with integers and use a Solidity compiler version below 0.8.0 because Solidity compiler 0.8.0 introduced default overflow and underflow checked arithmetic. Signed safe math library provides the same mathematical functions as safe math but for signed integers. The only operation that is missing is the modulus operation, which does not make sense for signed integers. The usage and the motivation for this is the same as safe math. Recall that Solidity allows both implicit casting of types and explicit casting between types. Explicit casting is where the developers can force the compiler to cast one type into another type, where the compiler may not be able to determine that it is safe to do so. In cases where the developers want to do what is known as downcasting, the OpenZeppelin SafeCast library provides various functions to do so in a safe manner. Downcasting is when the developer wants to cast a source type into a target type where the target type has fewer storage bits to represent it than the source type. So in such cases, because the target type has fewer storage bits, it may not always be safe to do so if the variable of that type actually requires the storage bits being reduced from the source type to destination type. SafeCast library provides functions that allow the developer to determine if that downcasting is safe, and if not, it raises an exception by reverting the transaction. There are various functions to safely downcast from unsigned integers of 256 bits to 224 bits, 128, all the way to 8 bits. And similarly, there are functions for signed integers to do so as well. So these functions become very useful for developers when they're doing downcasting to prevent overflows because of doing so. Recall that the mapping types in Solidity cannot be enumerated for all the keys and values that they contain. The Enumerable Map Library of OpenZeppelin allows a developer to create and use enumerable maps. Adding and removing entries from this mapping type can be done in constant time. Checking for existence of entries can also be done in constant time. Enumerating the maps can be done in order of n time, where n is the size of the mapping. And as of the latest version, the only supported mapping type is the one where keys are of UN256 and the values are of address type. The enumerable set library allows the developers to use enumerated sets. There are various functions that are provided to manage the sets. Adding and removing entries to the set and checking entries for existence again can be done in order of one time, that's constant time. Enumerating them can be done in order of n time. And as of the latest version, the only supported set types are those that contain bytes, addresses, or UN256. Bitmaps are commonly encountered data structures in computer science, where every bit of the underlying type can be thought of as representing a different variable. The Bitmaps library maps a UN256 type to Boolean types, where this bitmap can be used to represent 256 different Boolean values within that single UN256 type. And this library allows developers to do that in a very compact and efficient manner. The library provides 4 different functions to operate on these bitmaps. The get function returns the Boolean value at a particular index of the bitmap. The set_to function allows us to set the value at a particular index of that bitmap to the specified value. The set function sets the value of the bitmap at that index to 1, and unset sets the value of the index at that bitmap to 0.